Imagine standing on a frozen plain, the wind howling across an endless expanse of snow and grass. In the distance, a dark shape moves slowly against the white horizon, massive and deliberate. As it draws closer, you see the outline of enormous curved tusks, a towering domed head, and a body covered in thick, shaggy hair that sways with each step. This is a woolly mammoth, one of the most magnificent creatures ever to walk the earth, perfectly adapted to a world of ice and cold that no longer exists. Welcome to Bedtime Biology, where science meets serenity. Each night, we explore the quiet wonders of the natural world, calming your mind and sparking your curiosity. If you like these videos, please consider subscribing to the channel and commenting below if you have any feedback or suggestions for topics of future episodes. Tonight, we journey back through time to an age when glaciers covered much of the northern hemisphere, when vast herds of Ice Age giants roamed across landscapes we can barely imagine today. The woolly mammoth stands among the most iconic of all prehistoric animals, not only because of its impressive size and striking appearance, but because of how much we've learned about it. Frozen in the permafrost of Siberia for tens of thousands of years, woolly mammoths have emerged from the ice with their bodies remarkably intact, their last meals still preserved in their stomachs, their DNA waiting to tell stories of a vanished world. These creatures survived for hundreds of thousands of years in some of the harshest environments Earth has ever known, only to disappear just a few thousand years ago, when human civilizations were already building monuments and developing agriculture. The story of the woolly mammoth is a story of adaptation, of survival, of complex social bonds, and ultimately of loss. It's a reminder that even the most successful species, the ones that seem perfectly suited to their world, can vanish when that world changes too quickly. As we explore the life of these magnificent animals tonight, we'll discover how they lived, what they ate, how they raised their young, and what finally brought about their extinction. We'll visit the frozen tundra where they once grazed, examine the predators that hunted them, and marvel at the scientific discoveries that have brought them back to life in our imaginations. So, settle in, let your thoughts drift back through the millennia, and join us as we walk alongside the woolly mammoth through the snow and ice of the Pleistocene. When you picture a woolly mammoth, you might imagine a creature of tremendous size, something that dwarfed everything around it. The reality, though perhaps slightly less dramatic, is no less impressive. Woolly mammoths were roughly the same size as modern African elephants, which makes them large by any standard, but not the colossal giants that popular imagination sometimes portrays them to be. An adult male mammoth stood between 8.5 and 11 feet tall at the shoulder, with most individuals measuring somewhere around 9 to 10 feet. Females were smaller, typically reaching heights of about 7.5 to 9 feet. To put this in perspective, if a male mammoth stood beside a basketball hoop, his back would reach nearly to the rim. The weight of these animals matched their height. Males could weigh anywhere from 8,000 to 18,000 pounds, with most falling in the range of 9,000 to 13,000 pounds. That's roughly 4.5 to 6.5 tons, the weight of several cars. Females were lighter, typically weighing between 6,000 and 9,000 pounds. When a woolly mammoth calf was born, after a gestation period of about 22 months, similar to modern elephants, it weighed around 200 pounds, about the size of a large adult human. What truly distinguished woolly mammoths from their modern elephant relatives, what made them so perfectly suited to their frigid world, was not their size, but their remarkable adaptations to extreme cold. Every aspect of their body seemed designed for survival in sub-zero temperatures. Their most obvious adaptation was their coat, a thick layer of insulating fur that made them appear even larger than they actually were. The mammoth's coat consisted of 2 layers, a dense undercoat of fine wool, about an inch thick, and an outer covering of much longer guard hairs. These guard hairs could grow more than 2 feet long, with some reaching lengths of 3 feet, particularly along the flanks and belly, where they hung down like a shaggy skirt. This double-layered coat trapped air close to the body, creating an insulating barrier against the cold. The color of this fur varied from individual to individual, ranging from dark chocolate brown to lighter reddish brown, and even occasionally blonde. When we find mammoth hair preserved in the frozen ground today, it often appears orange or reddish, but scientists believe this is due to chemical changes that occurred during preservation, not the original color. Beneath this impressive coat of fur lay another crucial adaptation: the skin itself. Mammoth skin was extremely thick, measuring between half an inch and a full inch in thickness, similar to modern elephants. But unlike elephants, which need to keep cool in tropical climates, mammoths had an additional layer of protection. Directly under their skin, they carried a layer of fat that could be up to 4 inches thick. This subcutaneous fat served multiple purposes. It provided insulation, acting as a buffer against the cold. It stored energy for times when food was scarce, particularly during the long, harsh winters when vegetation was buried under deep snow. And it may have helped maintain body temperature by acting as a thermal reservoir. Scientists studying frozen mammoth carcasses have found this fat layer remarkably well preserved, still yellowish and intact after tens of thousands of years in the permafrost. The mammoth's head was distinctively shaped, high and domed, quite different from the flatter head profile of modern elephants. This domed shape resulted from the structure of the skull and the arrangement of air sinuses within it, which may have served to lighten the weight of the head while maintaining its strength. The high dome gave mammoths their characteristic silhouette, making them instantly recognizable even from a distance. Behind this domed head, the mammoth's back sloped downward toward the hindquarters, creating a profile that descended from the high shoulders to the lower rump. This sloping back was created by elongated spines on the front vertebrae, which supported a prominent shoulder hump. This hump, like the one found in camels, consisted largely of fat and served as an energy reserve, particularly important during winter months when food was harder to find. But perhaps the most striking features of the woolly mammoth were its tusks, those enormous curved ivory structures that have become synonymous with the species. Mammoth tusks were modified incisor teeth that grew continuously throughout the animal's life, emerging from the upper jaw and curving outward, then inward, and sometimes even crossing at the tips in old individuals. These tusks grew in a spiral pattern, with the left and right tusks twisting in opposite directions, creating a corkscrew effect that was unique to mammoths. In adult males, tusks typically measured between 8 and 9 feet along their outer curve, weighing around 100 pounds each. The longest tusk ever recorded measured over 13 feet and weighed more than 250 pounds, an absolutely massive structure that must have been both impressive and cumbersome for the mammoth that carried it. Female tusks were considerably smaller and thinner, usually measuring 5 to 6 feet in length and weighing only about 20 pounds each. The structure of these tusks tells us much about the mammoth's life. Like tree rings, mammoth tusks contain growth layers that represent periods of time, with each major layer corresponding to roughly 1 year. Narrower layers indicate periods of stress when food was scarce or the animal was sick or injured. By examining these growth patterns in cross-section, scientists can reconstruct the life history of individual mammoths, identifying years of hardship and years of plenty. The tusks were composed primarily of dentin, a material similar to bone, but denser and more durable, covered by a thin layer of cementum. About a quarter of each tusk's length was embedded in the skull, anchored in deep sockets, while the remainder protruded outward in that distinctive curve. These remarkable structures served multiple functions in the mammoth's daily life. Foremost among these was foraging. Mammoths used their tusks as tools to sweep away snow from the ground, exposing the vegetation buried beneath. Many preserved tusks show distinctive wear patterns, flat and polished sections on the underside, where they repeatedly scraped against ice and frozen ground. Some tusks bear scratches and gouges on their outer curvature, evidence of the hard work of digging through winter snow to reach buried grasses and shrubs. The tusks also helped mammoths strip bark from trees and dig up roots, functioning somewhat like a combination of shovel and crowbar. Beyond their utility in feeding, tusks played crucial roles in social and reproductive contexts. Male mammoths used their tusks in ritual combat, engaging in shoving matches and clashing that established dominance hierarchies and determined access to females. The curvature of the tusks, while impressive, made them unsuitable for stabbing, but they could be used for delivering powerful sideways blows and pushing. Fossil mammoth skeletons sometimes show evidence of shoulder blade injuries that likely resulted from being struck by another mammoth's tusk during these contests. The display of large, impressive tusks was also important for attracting mates, with females presumably favoring males with the largest and most symmetrical tusks. The mammoth's ears were another adaptation to the cold, much smaller than those of modern elephants. While African elephants have enormous ears that help them cool down by radiating heat, mammoths needed to conserve warmth, not lose it. Their ears measured only about a foot in length, a fraction of the size of their tropical cousins' ears. This reduced surface area meant less heat loss from blood flowing through the ear tissue. Similarly, the mammoth's tail was short and stubby, only about a foot long, compared to the long, swinging tails of modern elephants. The tail was covered with long hairs that extended beyond the actual tail length, giving it a fuller appearance while minimizing the amount of exposed skin. Under the tail, mammoths had a broad flap of skin that covered the anus, another adaptation to prevent heat loss from this vulnerable area. The mammoth's trunk, that remarkable flexible appendage inherited from its elephant ancestors, was as versatile and essential as it is in modern elephants. While no complete mammoth trunk has been preserved, cave paintings and frozen specimens that retained partial trunks reveal that it was similar in structure to a modern elephant's trunk. A muscular, boneless extension of the nose and upper lip, capable of extraordinary precision and power. The trunk ended in 2 finger-like projections that could grasp small objects with surprising delicacy. Mammoths use their trunks for countless tasks, pulling up tufts of grass, stripping leaves from shrubs, manipulating objects, drinking water, dusting themselves with dirt or snow for grooming, communicating through touch with other mammoths, and even disciplining young calves. A mammoth's trunk contained thousands of individual muscles that worked in coordination, allowing for movements ranging from the gentlest caress to the most powerful wrench. The mammoth's feet, like those of modern elephants, were specially adapted to support their tremendous weight while allowing them to walk relatively quietly. They walked on their toes, with their actual foot bones angled upward and supported by a thick pad of fibrous tissue and fat. This pad distributed the mammoth's weight over a larger surface area, preventing them from sinking deeply into soft ground and snow. Fossil trackways show that adult mammoths had a stride of about 6.5 feet, and when a herd moved, the adults walked at a pace that forced juvenile mammoths to trot or run to keep up, their shorter legs unable to match the steady gait of their elders. Inside the mammoth's body, there were additional adaptations to cold that weren't visible from the outside. Their blood carried hemoglobin, the protein that transports oxygen, with specific mutations that allowed it to function efficiently, even at very low temperatures. These mutations improved oxygen delivery throughout the body and helped prevent the blood from becoming too viscous in the cold. This was a crucial adaptation that allowed mammoths to remain active even when temperatures dropped far below freezing, maintaining the metabolic rate necessary to generate body heat. All of these adaptations, from the thick fur to the modified blood chemistry, worked together to create an animal superbly suited to life in the Ice Age world. The woolly mammoth was not just an elephant with fur. It was a highly specialized creature that had evolved over hundreds of thousands of years to thrive in one of the most challenging environments Earth has ever produced. Standing there in the frozen landscape, a mammoth must have seemed like a mountain of life, moving purposefully through a world of ice and snow that would have killed most other large mammals. Every aspect of its body told the same story. This was an animal built for the cold, adapted to survive where others could not, perfectly at home in a world that has long since vanished. To understand the woolly mammoth, we must understand the world it inhabited, a landscape so different from anything that exists today that it requires an act of imagination to visualize. This was the mammoth steppe, also called the tundra steppe, a vast grassland ecosystem that stretched across the northern hemisphere during the Pleistocene epoch. It was neither the barren, ice-covered wasteland that some might imagine when they think of the Ice Age, nor was it the lush forest or tropical savanna where modern elephants dwell. Instead, it was something unique, a cold, dry grassland, unlike any modern ecosystem. The mammoth steppe covered an enormous geographical area during the height of the last glacial period. It extended across much of Eurasia, from Western Europe through Siberia and into Alaska and northern Canada. At times, when sea levels were lower and more land was exposed, it stretched continuously across what is now the Bering Strait, creating a land bridge called Beringia that connected Asia and North America. This allowed woolly mammoths and many other Ice Age animals to migrate between continents, spreading their populations across the entire northern reaches of the world. The steppe occupied regions that today are covered by tundra, boreal forest, or are beneath the waters of shallow seas. Despite the cold temperatures that characterize the Ice Age, the mammoth steppe was not a frozen desert. The climate was cold and dry, dominated by high-pressure systems that brought clear skies and relatively light snowfall. Winter temperatures could plummet to extreme lows, but the dry conditions meant that snow didn't accumulate to the depths that would have made the landscape completely inaccessible to grazing animals. In summer, temperatures rose enough to melt most of the winter snow and allow plants to grow vigorously, though it never became truly warm. This created a seasonal rhythm that structured the entire ecosystem. The vegetation of the mammoth steppe was remarkably rich and diverse for such a cold environment. The landscape was dominated by a mixture of grasses and sedges, those grass-like plants that thrive in wet or marshy areas. These formed extensive carpets that provided abundant food for grazing animals. Mixed among the grasses were countless species of forbs, small flowering plants that included buttercups, various legumes, and other herbaceous species. These forbs were particularly important because they were highly nutritious, packed with proteins and nutrients that helped animals survive in the demanding environment. Scattered across the landscape were dwarf shrubs, including willows, birch, and alder, which grew low to the ground but provided important browse, especially during winter, when other food sources were less available. Mosses covered many surfaces, adding to the vegetative diversity. What made the mammoth steppe so productive was the richness of its soil and the rapid growth of its plants. The cold, dry climate and the constant grazing and trampling by large herbivores prevented trees from becoming established, keeping the landscape open and allowing sunlight to reach ground-level plants. The soil was enriched by the decomposition of plant matter and the waste products of the vast herds that lived there. The constant presence of large grazing animals actually helped maintain the productivity of the steppe. By eating plants, they recycled nutrients back into the system through their dung. By trampling the ground, they broke up the soil surface and pressed seeds into the earth, facilitating germination. By preventing woody plants from taking over, they maintained the grassland character of the ecosystem. This was not a silent, empty landscape. The mammoth steppe teemed with life beyond the woolly mammoths themselves. Herds of woolly rhinoceroses, massive creatures covered in thick fur and bearing enormous horns, shared the grazing grounds with the mammoths. Wild horses, smaller and stockier than their modern descendants, moved in swift herds across the plains. Massive bison with enormous curved horns grazed alongside smaller animals. Reindeer, known as caribou in North America, formed huge migratory herds. Musk oxen, with their long, shaggy coats and powerful builds, clustered together for protection. Saiga antelope, with their distinctive enlarged noses that warmed the cold air they breathed, bounded across the landscape. Among these, herbivores moved predators, creating the dynamic interplay of life and death that characterizes any ecosystem. Cave lions, larger than modern lions and adapted to the cold, stalked the herds. Packs of wolves, larger and more robust than today's wolves, hunted cooperatively. Cave hyenas scavenged and occasionally hunted in their own right. Enormous, short-faced bears, standing taller than any modern bear, dominated as apex predators. And increasingly, as time went on, humans moved across this landscape as well. Bands of hunters following the herds, their presence gradually expanding as their hunting technologies improved. The daily and seasonal rhythms of the mammoth steppe shaped every aspect of life there. In summer, when the sun barely set at high latitudes, the steppe burst into life. grasses grew rapidly, flowers bloomed in profusion, and the herbivore populations swelled as new calves and foals joined the herds. This was the season of plenty, when mammoths and other grazers could feed almost constantly, building up the fat reserves they would need to survive the coming winter. The long days meant extended feeding time, allowing animals to consume enormous quantities of vegetation. As summer faded into autumn, the plant growth slowed, and animals began their preparations for winter. Some species, like the reindeer, migrated southward to more favorable areas. Others, like the mammoths, prepared to endure the winter where they were. The changing angle of the sun signaled hormonal changes in many animals, triggering breeding behaviors and other seasonal adaptations. The landscape slowly transformed from green and flowering to brown and dormant. Winter on the mammoth steppe was harsh, but not impossibly so. Temperatures dropped dramatically, and snow covered the ground. But the relatively light snowfall and the wind that constantly swept the exposed areas meant that vegetation remained accessible to determined grazers. Mammoths used their tusks to sweep snow aside, exposing the dried grasses and shrubs beneath. They fed on willow and birch twigs when other food was scarce, using their trunks to strip bark from branches. The thick layer of fat under their skin sustained them through periods when feeding was particularly difficult. The long winter nights were times of minimal activity when conserving energy was paramount. Then spring arrived, the snow melting away to reveal the landscape renewed. This was perhaps the most challenging time of year for many animals, when winter food supplies had been exhausted, but new growth had not yet begun in earnest. Studies of mammoth remains show that many died in late winter or early spring, their fat reserves depleted, unable to survive until the season turned. But for those who made it through, spring brought renewal, the return of green growth, and the birth of new calves. The mammoth steppe was not uniform across its vast range. Regional variations created slightly different ecosystems in different areas. Western European mammoths lived in somewhat warmer conditions than their Siberian counterparts, and may have had slightly less shaggy coats. Mammoths in North America encountered different plant communities and different predator pressures. Some populations inhabited areas near forests, while others lived in the most open, treeless expanses. But across all these variations, the fundamental character of the ecosystem remained the same: a cold, dry grassland supporting enormous biomass of large herbivores, including the majestic woolly mammoth. This world, so productive and so full of life, would not last forever. As the climate began to change, as temperatures rose and precipitation patterns shifted, the mammoth steppe began to transform. The changes were gradual at first, but accelerating, and they would ultimately prove fatal, not only to the ecosystem itself, but to many of the magnificent animals that had evolved to live there. But for hundreds of thousands of years, the mammoth steppe was home, the stage upon which the drama of Ice Age life unfolded, and the woolly mammoth was one of its greatest stars. A woolly mammoth's life revolved around a single overriding necessity: eating. The demands of maintaining a body weighing several tons in a cold environment meant that feeding occupied most of every mammoth's waking hours. Scientists estimate that an adult mammoth needed to consume between 180 and 400 pounds of plant matter every day, depending on its size, the season, and the quality of available food. To put this in perspective, that's roughly equivalent to eating several hundred to nearly 1,000 large heads of lettuce daily. Achieving this intake required feeding for up to 20 hours per day, leaving only brief periods for rest and social activities. The mammoth was primarily a grazer, focusing its feeding efforts on the grasses and sedges that carpeted the mammoth steppe. These plants formed the foundation of its diet, the bulk of what it consumed throughout most of the year. Different species of grasses grew across the landscape, and mammoths were not particularly selective, consuming whichever species were most abundant and accessible. Sedges, those grass-like plants that typically grow in wetter areas and along watercourses, provided an important alternative to grasses, especially in areas where soil moisture was higher. These plants, while not as nutritionally rich as some other foods, were abundant and available, and their high fiber content was well suited to the mammoth's digestive system. But grasses and sedges alone did not provide complete nutrition. Interspersed with these dominant plants were forbs, those small flowering plants that added crucial variety to the mammoth's diet. Forbs included species like buttercups, various types of clover and vetch, cinquefoil, and many other herbaceous plants. These were particularly valuable because they contained higher concentrations of proteins, vitamins, and minerals than grasses. Recent research has suggested that forbs may have been more important in the mammoth diet than previously recognized, with some studies indicating they could have comprised a significant portion of the food intake during certain seasons. The bright flowers of many forb species may have served as visual cues, helping mammoths locate these nutritious plants among the surrounding grasses. Woody vegetation also played a role, though a less prominent one. Dwarf shrubs, particularly willows and birches, grew scattered across the landscape, and mammoths fed on these when they were available. They used their trunks to grasp branches, and their tusks to strip away bark, accessing the nutritious cambium layer underneath. The buds, leaves, and tender shoots of these woody plants were especially valuable in spring, when they represented some of the first fresh growth of the season. In winter, when grasses were buried under snow or dried to brown stubs, woody browse became more important, providing essential nutrients during the leanest time of year. The mammoth's diet varied considerably with the seasons, a pattern revealed by analysis of preserved stomach contents and fossilized dung. In summer, when plant growth was at its peak, mammoths had access to a bounty of fresh, green vegetation. They could afford to be somewhat selective, choosing the most nutritious plants and the freshest growth. The long summer days allowed extended feeding time, and mammoths took full advantage, building up fat reserves for winter. The diversity of their summer diet was remarkable, with studies of gut contents showing dozens of different plant species consumed. As autumn arrived and plant growth slowed, the diet shifted toward more mature, tougher vegetation. Seeds and seed heads became important components of the diet, providing concentrated nutrition. The mammoths began to focus more on the woody plants, stripping bark and browsing on shrubs as herbaceous plants died back. This transitional period was crucial for putting on the last reserves of fat before winter's full arrival. Winter brought the greatest dietary challenges. Snow covered much of the vegetation, though the relatively light snowfall and constant wind meant that some areas remained accessible. Mammoths used their tusks as snow shovels, sweeping aside the white covering to reach the dried grasses beneath. Wear patterns on preserved tusks show flat, polished areas up to a foot long where they repeatedly scraped against frozen ground. The winter diet consisted largely of dried grass stems, sedges, and whatever woody vegetation was accessible. Willow and birch became particularly important during these months. Mammoths also fed on moss, which remained accessible under the snow, and provided at least some nutritional value when other food was scarce. Spring was perhaps the most difficult season. Winter food supplies were exhausted, fat reserves depleted, but new plant growth had not yet begun in earnest. This was the season when mortality was highest among mammoths, as evidenced by growth rings in tusks that show slowed growth during late winter and early spring. Young mammoths, elderly individuals, and any animal weakened by injury or illness faced the greatest risk during this hungry gap. But for those who survived, spring also brought renewal, the first green shoots pushing through the soil, the buds swelling on shrubs, and the promise of summer's abundance ahead. The process of actually gathering and consuming all this food required specialized anatomical features. The mammoth's trunk was its primary feeding tool, that remarkably versatile appendage that could perform tasks requiring either great power or extraordinary delicacy. When feeding on grass, a mammoth would wrap its trunk around a tuft of the vegetation, pulling upward to tear the plants free from their roots or break them off at ground level. The trunk's two finger-like projections at the tip allowed it to grasp even individual grass stems. For feeding on trees and shrubs, the trunk could strip leaves from branches or grip branches to bend them within reach of the mouth, where the tusks could then be used to strip bark or break off pieces. Once food was gathered, the real work of digestion began, and here the mammoth's teeth played the crucial role. Like modern elephants, mammoths had an unusual dental system. They had only 4 active teeth at any time, 1 in each quadrant of the jaw, but these teeth were massive and highly specialized for grinding tough plant material. Each tooth was composed of multiple plates of enamel, the hard outer surface of teeth, separated by dentin and held together by cementum. These plates formed ridges that ran perpendicular to the direction of jaw movement, creating an efficient grinding surface. As a mammoth chewed, the ridges on the upper and lower teeth slid past each other in a front-to-back motion, shearing and grinding the plant material between them. This dental arrangement was beautifully adapted to the mammoth's diet of tough, abrasive grasses and sedges. These plants contain silica, tiny particles of glass-like material that rapidly wears down teeth. The mammoth's teeth were designed to handle this wear. As the grinding surface wore down, new tooth material was continuously pushed up from below, and the teeth slowly moved forward in the jaw. When a tooth became too worn, it fell out the front of the mouth, and a new tooth, which had been developing behind it, moved forward to take its place. This process of tooth replacement happened 6 times during a mammoth's life. Each successive tooth was larger than the one before, suitable for the growing jaw of the maturing animal. When the 6th and final set of teeth was worn down, the mammoth could no longer feed efficiently, and starvation became likely. This limitation on tooth replacement was one of the primary factors determining the maximum lifespan of mammoths. The mammoth's digestive system worked constantly to process the enormous quantities of plant material it consumed. Like modern elephants, mammoths were hindgut fermenters, meaning that most of the bacterial breakdown of plant fibers occurred in the large intestine and cecum, rather than in a multi-chambered stomach like cattle have. This system is less efficient than that of ruminants, extracting less nutrition from each mouthful of food, but it allows for faster processing, letting the animal consume larger quantities. Scientists have found mammoth dung, fossilized or preserved in ice, that provides remarkable insights into this digestive process. The preserved feces often still contain identifiable plant fragments, stems and leaves that retained their structure even after passing through the mammoth's digestive tract. The presence of these fragments shows that, like elephants, mammoths didn't completely break down their food, instead processing large volumes rapidly. Young mammoths had a different dietary relationship with their mothers. Newborn calves fed exclusively on their mother's milk for the first months of life, and nursing continued for several years. Analysis of tooth growth patterns suggests that mammoth calves nursed for at least 3 years, and possibly as long as 5. This extended nursing period was longer than in modern elephants, and may reflect the challenges of living in the harsh Ice Age environment. While still nursing, young mammoths began to learn about solid food, observing their mothers and other herd members to learn which plants were good to eat and how to gather them. In a particularly revealing finding, scientists discovered that young mammoths, like young elephants today, ate their mother's dung. This behavior, far from being simply youthful curiosity, served an important purpose. It introduced beneficial bacteria into the calf's digestive system, the microorganisms necessary for breaking down plant fibers. The bacteria passed from mother to offspring through this fecal consumption, establishing the gut microbiome that would allow the young mammoth to digest plant material once it was weaned. The mammoth's role as a grazer had profound effects on the ecosystem itself. By consuming enormous quantities of vegetation, mammoths and the other large herbivores prevented trees from taking over the landscape, maintaining the open grassland character of the steppe. Their dung fertilized the soil, recycling nutrients and enriching plant growth. Their trampling broke up soil crusts and pressed seeds into the ground, actually promoting plant diversity and productivity. In this way, mammoths were not just passive consumers of the landscape, but active engineers of it, helping to maintain the very ecosystem that sustained them. When they disappeared, the character of northern landscapes changed fundamentally. Forests spreading where grasslands had once stretched to the horizon. The daily rhythm of feeding, the seasonal variations in diet, the specialized tools and techniques for gathering and processing food. All of these patterns defined the mammoth's existence as much as any other aspect of its biology. In the eternal struggle for survival, eating was paramount, the foundation upon which all else rested. A mammoth that fed well could survive the winter, could grow strong, could reproduce and raise young. A mammoth that failed to feed adequately faced weakness, illness, and death. The simple act of eating, repeated thousands of times each day across hundreds of thousands of years, was what made the woolly mammoth one of the most successful large mammals of the Ice Age. Woolly mammoths were not solitary wanderers across the Ice Age landscape. They were deeply social animals who lived in complex family groups, communicated with each other through sounds and touch, and maintained relationships that could last a lifetime. Everything we know from fossil evidence, from cave paintings created by ancient humans who observed them, and from comparison with modern elephants, points to mammoths having rich social lives built around strong family bonds and shared knowledge passed from generation to generation. The basic unit of mammoth society was the matriarchal herd, a family group led by the oldest and most experienced female. This matriarch, typically 50 to 60 years old, was the repository of the group's collective wisdom. She knew where to find food during different seasons, where water sources could be found, which routes were safest for travel, and how to respond to various dangers. Her experience, accumulated over decades of life in the challenging Ice Age environment, was crucial to the survival of the entire group. When the matriarch moved, the herd moved. When she stopped to rest or feed, they stopped. When she determined it was time to migrate to new feeding grounds, they followed. The composition of these family herds was similar to what we observe in modern elephant societies. The core of the group consisted of related females, the matriarch herself, her daughters, her sisters, and their daughters. Young mammoths of both sexes remained with their mothers' herds while they were juveniles. The size of these family groups varied, but fossil evidence suggests they typically contained between 6 and 15 individuals, though they could occasionally be larger. Cave paintings from Europe sometimes depict groups of mammoths, and these artistic representations, created by people who actually observed living mammoths, show clusters of animals that seem to match this size range. Within the herd, relationships were complex and nuanced. Mothers and their calves maintained the closest bonds, staying near each other almost constantly during the first years of the calf's life. Young mammoths spent their early years learning everything they needed to know to survive. Which plants were good to eat and which should be avoided. How to use their trunks effectively for feeding and drinking. How to interpret different sounds and body language signals from other mammoths. And how to respond to various threats. This learning took place through observation and imitation, with young mammoths watching their mothers and the other adult females in the group. Adult females in the herd cooperated in raising young, not just their own offspring, but the calves of their relatives as well. This communal care meant that if a mother was injured, sick, or killed, her calf might still survive under the care of aunts or older sisters. Young females remained with their natal herds throughout their lives, learning from older females and eventually becoming mothers themselves, then grandmothers, contributing their own knowledge and experience to the collective wisdom of the group. The oldest females, who no longer bore young themselves, still played vital roles as teachers and guides. For young males, however, this pattern changed as they approached maturity. At around 10 years of age, roughly when they reached physical maturity, male mammoths left their mothers' herds. This departure wasn't necessarily hostile or abrupt, but it was definitive. Young males might linger near their natal herd for a time, gradually spending more and more time apart, eventually establishing complete independence. This pattern of male dispersal served an important evolutionary function, preventing inbreeding and ensuring genetic diversity in the population. After leaving their mothers' herds, male mammoths typically led more solitary lives, or they formed loose associations with other males. These bachelor groups were much less cohesive than the female-led family herds. Males might travel together for a time, then separate, then perhaps rejoin or associate with different males. The bonds between males were not as strong or enduring as those between related females. Adult males spent most of their time alone or in these temporary associations, feeding extensively to maintain their larger body size and preparing for the seasonal challenges of reproduction. The breeding season brought temporary changes to this social structure. During this time, which likely occurred in late summer or autumn, based on the spring birth season, observed in preserved specimens, males sought out females in breeding condition. Adult males engaged in dramatic displays and sometimes violent contests to establish dominance and gain access to receptive females. These contests involved impressive displays of size and strength, with males facing each other and using their massive tusks to push and shove, each trying to force the other to give way. The sound of these confrontations, the impact of several tons of mammoth pushing against several tons of mammoth, must have carried across the landscape. Injuries sometimes resulted, and fossil shoulder blades occasionally show damage that appears to have come from being struck by another mammoth's tusk during these battles. Males also experienced a physiological state known as musth, similar to that seen in male elephants today. During musth, which likely occurred seasonally in mature males, hormone levels surged, leading to increased aggression and a single-minded focus on finding and mating with females. Musth males secreted fluid from temporal glands located on the sides of their heads, and this fluid likely carried chemical signals that communicated their reproductive state to other mammoths. Musth was energetically demanding and potentially dangerous, as males in this state were more likely to engage in serious fights and took greater risks. But for males who successfully navigated this period, the reward was the opportunity to mate and pass on their genes to the next generation. After mating, females underwent a gestation period of approximately 22 months, similar to modern elephants. This long pregnancy meant that a female could only produce a calf every 4 to 5 years at most, and in practice, the interval was often longer. Birth likely occurred in spring, when fresh plant growth provided nursing mothers with the nutrition they needed to produce milk. A newborn mammoth, weighing around 200 pounds, was immediately mobile, able to stand and walk within hours of birth, a necessity in an environment where predators were always a threat. The birth of a calf was a major event in the life of the herd. The mother received support from other females, who helped protect and guide the newborn during its first vulnerable days. The calf's first year was a time of rapid learning and growth, the foundation for all its future development. It learned to use its trunk, initially a clumsy and poorly controlled appendage that the calf sometimes stepped on or swung randomly, but gradually becoming a versatile tool. It learned to feed, first by nursing, then slowly incorporating plant material into its diet. And it learned the social rules of the herd, how to interact appropriately with different individuals, how to recognize dominance relationships, and how to respond to the matriarch's guidance. Communication among mammoths involved multiple sensory channels. They almost certainly produced a variety of sounds, from low rumbling vocalizations that could travel for miles across the landscape to higher pitched calls. Modern elephants use infrasound, vocalizations below the range of human hearing, to communicate over long distances, and mammoths likely had similar capabilities. These low-frequency sounds can travel for several miles, allowing widely separated individuals or groups to maintain contact. The rumbles may have conveyed information about identity, location, and emotional state. Touch was another crucial form of communication. Mammoths likely used their trunks to touch and caress each other, reinforcing social bonds and providing comfort. A mother might run her trunk along her calf's back, or two adult females might intertwine their trunks in what appears, in elephant behavior, to be a gesture of affection and reassurance. During greetings, mammoths may have touched each other with their trunks, similar to how humans shake hands or embrace. Smell, too, played a role, with the trunk serving as a highly sensitive organ for detecting chemical signals in the environment and from other mammoths. The death of a herd member, particularly the matriarch, was likely a significant event. Based on elephant behavior, mammoths may have shown interest in the bodies of dead relatives, touching them with their trunks and perhaps lingering near them for a time. Whether this represented grief in a sense that humans would recognize, or simply curiosity and confusion at the absence of a familiar individual, we cannot know with certainty. But the evidence suggests these were animals capable of recognizing individuals, forming long-term relationships, and responding to the loss of group members. The social structure of mammoth herds was not just a pleasant arrangement, but a crucial survival strategy. The knowledge held by older, experienced females was invaluable in a challenging and variable environment. A matriarch who had lived through multiple severe winters knew how to find food when snow was deep, where to shelter from storms, and how to lead the herd to safety when conditions became dangerous. Young mammoths benefited from the protection and teaching of multiple adults. The cooperative structure of the herd allowed for collective defense against predators and collective child rearing that increased the survival rate of calves. This social complexity, these enduring relationships, and shared knowledge made mammoths more than just large herbivores. They were intelligent, emotionally complex creatures who lived in a web of relationships, who learned from their elders and taught their young, who cooperated and communicated. When we think of the woolly mammoth, we should remember not just the shaggy coat and curved tusks, but also these invisible bonds that connected individuals across generations. The social fabric that made them, in a real sense, more than the sum of their parts. For all their size and strength, woolly mammoths did not live in a world free from danger. The mammoth steppe was home to an array of predators, hunters who specialized in bringing down large prey, and young, old, sick, or injured mammoths could fall victim to these formidable carnivores. The dynamic between predator and prey shaped the behavior and ecology of both, creating patterns of vigilance, defense, and sometimes violent conflict on the frozen plains. The most formidable predators that stalked woolly mammoths were the large cats of the Ice Age. The cave lion, known scientifically as Panthera spelaea, was larger than modern lions and perfectly adapted to the cold environment. Males could weigh over 700 pounds, with powerful jaws and muscular builds that made them capable of bringing down massive prey. These lions likely lived in social groups, prides similar to those of modern lions, and they hunted cooperatively, using coordinated tactics to overwhelm animals much larger than themselves. For adult mammoths in good health, a cave lion pride represented a threat, but not an overwhelming one. The sheer size difference was substantial. An adult mammoth weighed many times what even the largest lion weighed, and its tusks, trunk, and bulk made it dangerous to attack. But young mammoths, particularly calves in their first year or two of life, were vulnerable. A calf might weigh only a few hundred pounds, small enough that a coordinated attack by several lions could bring it down. For a pride of hungry lions, a mammoth calf represented a large meal, worth the risk of attacking despite the fierce defense that the calf's mother and the other adult females in the herd would mount. The defense strategy employed by mammoth herds when faced with predators like cave lions was one of collective protection. When threatened, adult mammoths would form a defensive circle or wall, placing the calves in the center and presenting a barrier of massive bodies, swinging trunks and sharp tusks to any predator that approached. This formation, observed in fossil trackways and inferred from modern elephant behavior, was highly effective. A cave lion facing a wall of several adult mammoths, each weighing multiple tons and equipped with powerful defensive weapons, would find few opportunities for a successful attack. The adults could use their tusks to gore or strike at attacking predators, and their trunks could deliver powerful blows. Simply being stepped on by a mammoth would be fatal for a lion. But predators are patient and opportunistic. They would watch a herd, looking for moments of vulnerability. A calf that strayed too far from the protective adults, perhaps distracted by play or curious about something in the environment, might suddenly find itself isolated. A mammoth, weakened by age or illness, might struggle to keep up with the herd, falling behind where it could be more easily targeted. An individual that became mired in mud or fell through thin ice over a lake or river could find itself helpless, unable to use its size and strength effectively. It was in these moments that predators struck. Wolves presented a different kind of threat. The dire wolves of the Ice Age were larger and more robust than modern grey wolves, with powerful jaws capable of crushing bone. Like modern wolves, they were pack hunters who used cooperation and persistence to bring down prey much larger than themselves. A pack of dire wolves would harry a mammoth over a long period, nipping at its legs and flanks, exhausting it through blood loss and fatigue, waiting for it to weaken enough that they could move in for the kill. Adult mammoths in good condition could defend against wolf packs, and a mammoth surrounded by its herd was relatively safe. But an isolated individual, especially one already weakened, faced a much greater threat. Cave hyenas, large and powerful scavengers and hunters, also played a role in mammoth mortality. While they likely preferred to scavenge already dead carcasses, they were capable hunters in their own right and would attack vulnerable individuals. Their incredibly powerful jaws, capable of crushing bones to extract marrow, made them effective at processing even the largest carcasses. A group of cave hyenas could pose a serious threat to a young or weakened mammoth. The short-faced bear, one of the most imposing predators of the Ice Age in North America, stood taller than any modern bear when on its hind legs and possessed enormous strength. These bears were likely omnivorous, but certainly capable of killing large prey. A short-faced bear encountering a young mammoth might well attempt to take it down, using its size and power to overwhelm the calf, despite the defensive efforts of adult mammoths. Beyond these large predators, mammoths faced threats from their environment itself. Accidents were probably a significant source of mortality. A mammoth could fall through ice while crossing a frozen river or lake, unable to escape and drowning or dying from hypothermia. They could become stuck in mud, particularly in marshy areas or along riverbanks where the soil was soft. Once mired, even the strongest mammoth might be unable to free itself, eventually dying from exposure, starvation, or predation. Some of the best preserved mammoth fossils come from individuals who died in exactly this way, their bodies rapidly buried by sediment that later froze, preserving them for tens of thousands of years. Disease and parasites, though they leave little trace in the fossil record, undoubtedly took their toll as well. Internal parasites could weaken an animal, making it more susceptible to predation or environmental stresses. Bacterial or viral diseases could sweep through populations, particularly affecting the young, old, or already weakened. Injuries were another risk. A mammoth could break a leg in a fall or misstep, and such an injury in a multi-ton animal would be catastrophic. Unable to keep up with the herd and unable to feed effectively, an injured mammoth would weaken quickly and become easy prey. Arthritis and other age-related conditions, evident in some fossil bones, could progressively limit an older mammoth's mobility. The seasonal rhythms of the environment created periods of greater and lesser risk. Late winter and early spring, when food was scarce and fat reserves were depleted, was the most dangerous time. Mammoth tusks show growth rings that reveal these seasonal stresses, periods when growth slowed or nearly stopped as the animal struggled to survive. It was during these hungry months that predators had their greatest advantage, when weakened mammoths were less able to defend themselves and less able to keep up with their herds. Despite all these threats, adult mammoths in their prime were remarkably resilient. Fossil evidence shows that many individuals survived serious injuries that today would seem fatal. Broken bones that healed, leaving evidence of the injury in the form of thickened bone or misalignment. Infections that an individual somehow overcame. Encounters with predators that left scars but not death. This resilience, combined with the protection offered by the herd structure and the mammoth's own formidable defenses, meant that mammoths who survived the vulnerable years of early life had a good chance of living for decades. The relationship between mammoths and their predators was part of the larger web of life on the mammoth steppe. Predation controlled population sizes, removed sick and weak individuals who might otherwise spread disease, and recycled nutrients when scavengers fed on carcasses. The presence of predators also shaped mammoth behavior, encouraging the maintenance of close social bonds and vigilant group defense. In this way, predator and prey evolved together, each influencing the other's evolution across thousands of generations. But there was one predator whose relationship with the mammoth would prove different from all the others, one whose impact would eventually prove catastrophic. That predator was human, and the story of humans and mammoths is complex, involving not just hunting, but also a degree of cultural fascination and artistic representation that suggests these two species saw each other in ways that went beyond simple predator and prey. Among the most remarkable aspects of woolly mammoth biology is not something about the living animals themselves, but rather what happened to some of them after death. In the frozen ground of Siberia, Alaska, and other northern regions, mammoths who died thousands of years ago have been preserved in a way that is almost unheard of for creatures this large and this ancient. These frozen specimens have revolutionized our understanding of mammoths, providing information that could never be obtained from bones alone. The preservation of woolly mammoths in permafrost is not common, but it happens often enough that new specimens are discovered every few years. The process requires a very specific set of circumstances. A mammoth must die in or near a location where rapid burial and freezing can occur. This might happen if the animal becomes mired in mud along a riverbank, drowns in a lake or pond, or falls into a crevasse. the body must be quickly covered by sediment and frozen before decomposition can destroy the soft tissues. Once frozen, the body must remain continuously frozen for thousands of years. If it thaws and refreezes, much of the preservation will be lost as decay processes resume during the thawed periods. The result, when all these conditions are met, is extraordinary. Mammoths have been found with their skin intact, their internal organs preserved, even the contents of their stomachs still identifiable. Hair remains attached to the hide, sometimes in thick mats. Fat tissue under the skin retains its original structure. In the most exceptional cases, scientists have been able to examine everything from the structure of individual cells to the DNA within them. One of the most famous of these discoveries occurred in 2007, when a reindeer herder in northern Siberia found something remarkable eroding out of the riverbank along the Urubay River. It was a baby mammoth, preserved in nearly perfect condition. The calf, later named Lyuba after the herder's wife, had died approximately 41,800 years ago, at only about 1 month of age. She was so well preserved that she appeared almost lifelike, with her eyes closed as if sleeping, her trunk curled under her head, even her eyelashes still in place. Clumps of reddish-brown wool clung to her wrinkled skin. Lyuba's discovery provided scientists with unprecedented opportunities to study mammoth biology. CT scans revealed her internal anatomy in detail, showing organs, bones, and soft tissues that no one had seen intact before. Her stomach contained identifiable milk and some plant material, and remarkably, also contained fecal matter from an adult mammoth, almost certainly her mother. This fecal material provided direct evidence that mammoth calves, like young elephants, ate their mother's dung to acquire the gut bacteria necessary for digesting plant material later in life. Analysis of her teeth and growth patterns revealed that she had been born in spring, the season when fresh plant growth would provide nursing mothers with abundant food. Chemical analysis of her body tissues provided information about what her mother had been eating and about the environment in which they lived. The cause of Lyuba's death was also apparent from examination of her remains. Sediment filled her trunk, mouth, and windpipe, blocking her airways. She likely became mired in mud, perhaps along the edge of a marsh or muddy stream, and suffocated. The same mud that killed her also preserved her, creating an oxygen-free environment that prevented bacterial decay. Subsequent rapid freezing and burial in permafrost ensured her preservation for tens of millennia. Lyuba is not unique, though she is one of the best preserved mammoth specimens ever found. Another juvenile mammoth, named Yucca, was discovered in 2010 in Siberia. Yucca was slightly older than Lyuba at the time of death, approximately 6 to 8 years old. This specimen also showed excellent preservation, with muscle, tissue, organs, and even liquid blood still present in the carcass when it was first examined. Evidence suggested Yucca had been attacked by predators, possibly cave lions, though whether this attack was the cause of death or occurred shortly after death from other causes remained unclear. Adult mammoth specimens have also been found frozen in the permafrost. The Yucca mammoth, discovered in 2002, consisted of the head, tusks, and front legs of an adult male. The head was entirely covered with skin and remarkably well preserved, allowing scientists to study the structure of the temporal glands, the shape of the trunk, and other features rarely preserved. The tusks were enormous, and growth pattern analysis revealed the mammoth had been approximately 47 to 49 years old at death. Examination of gut contents showed that the mammoth's last meal had consisted primarily of grass stems from the family Poaceae. And remarkably, these plant fragments had retained their colour and structure even after 22,500 years. These frozen specimens have allowed scientists to study aspects of mammoth biology that could never be determined from skeletons alone. The structure and layering of the fur, the thickness of the skin, the depth of the fat layer, the colour of the hair, the arrangement of internal organs, all of these details came from frozen specimens. DNA has been extracted from mammoth tissue, allowing for genetic studies that have revealed the evolutionary relationships between different mammoth populations, the degree of genetic diversity in populations, and even some of the specific genetic adaptations that allowed mammoths to survive in cold environments. The hemoglobin gene, for instance, shows mutations that improved oxygen transport in cold conditions. Genes related to fat deposition, hair growth, and other cold-adapted traits have been identified through comparison with elephant genomes. The scientific value of these specimens cannot be overstated. Each new discovery adds to our understanding of these remarkable animals. But there is also something deeply moving about encountering these ancient creatures so well preserved. When scientists first saw Liuba, several described the experience in emotional terms, noting how it felt, as if the baby mammoth had just fallen asleep. There is something profound about seeing not just bones, but actual flesh and blood, hair and skin, from an animal that lived tens of thousands of years ago. It connects us to the reality of these creatures in a way that fossilized bones, as informative as they are, cannot quite achieve. The continued discovery of frozen mammoths also serves as a reminder of climate change. As Arctic regions warm, permafrost that has been continuously frozen for thousands of years is now thawing. This reveals more mammoth remains, but it also means that some frozen specimens may be lost to decay before they can be studied. The same warming that reveals these ancient treasures also threatens to destroy them, a poignant parallel to the role that climate change played in the extinction of the mammoths themselves. Every frozen mammoth tells a story. Liuba's story is of a young calf who became separated from her mother for just long enough to blunder into danger, dying alone in the mud. Yuka's story involves an encounter with predators in the final hours of life. The Yukagir mammoth's story is of a mature male who died in winter or early spring, the most difficult season. These individual narratives, preserved in tissue and bone, connect us across the millennia to specific moments in the lives of actual animals. They remind us that the mammoths we study were not abstractions, but living beings who experienced their world, who felt hunger and cold, who had relationships with other mammoths, who struggled to survive in a challenging environment. The frozen specimens preserve not just bodies, but these individual stories, fragments of experience from a vanished world. For hundreds of thousands of years, woolly mammoths were among the most successful large mammals on Earth. They thrived across vast stretches of the Northern Hemisphere, from Western Europe to Alaska, adapting to some of the harshest environments the planet had to offer. Their populations numbered in the millions at their peak. And then, in what is, geologically speaking, the blink of an eye, they were gone. The extinction of the woolly mammoth is one of the great mysteries of prehistoric biology, a puzzle that has generated fierce debate among scientists for more than a century. What killed the mammoths? The answer, it turns out, is both simpler and more complicated than a single cause. The story of mammoth extinction is part of a larger pattern of megafauna extinction that occurred at the end of the Pleistocene epoch and the beginning of the Holocene, the current epoch in which we live. Across the world, large animals began to disappear. In North America, mastodons, giant ground sloths, saber-toothed cats, giant short-faced bears, American lions, camels, horses, and many others went extinct. In Eurasia, the woolly rhinoceros, cave lions, cave bears, and giant deer disappeared. In South America, Australia, and on islands around the world, similar waves of extinction eliminated entire groups of large animals. The woolly mammoth was part of this global die-off, but the timing and pattern of mammoth extinction provides clues about what caused it. The first and most obvious factor was climate change. The last glacial period, the most recent major ice age, began to end around 15,000 years ago. Temperatures started to rise, glaciers began to melt, and the landscape began to transform. The mammoth steppe, that productive grassland ecosystem that had supported such enormous biomass of large herbivores, started to change in fundamental ways. As temperatures increased, precipitation patterns shifted, bringing more moisture to many northern regions. This sounds benign, but for the mammoth steppe, it was catastrophic. The increased moisture led to the formation of lakes, rivers, marshes, and wetlands where dry grassland had previously existed. The vegetation changed. Trees began to spread, forests expanding into areas that had been open steppe. The grasses and forbs that mammoths depended on were replaced by mosses, shrubs, and eventually trees. This new vegetation was less nutritious and less abundant. The biomass of plant matter available to support large herbivores decreased dramatically. Essentially, the mammoth's habitat was disappearing, replaced by ecosystems that could not support such large populations of massive grazers. The speed and scale of this transformation were remarkable. Climate models and fossil evidence show that suitable mammoth habitat declined by about 90% between 42,000 years ago and 6,000 years ago. What had once been a nearly continuous belt of grassland stretching across the northern continents became fragmented into isolated patches, mostly in Arctic Siberia and the northernmost reaches of North America. Mammoth populations, which had been interconnected across vast ranges, became isolated in these refuge areas. Population sizes crashed as available habitat shrank. This habitat loss placed mammoths under tremendous pressure. Food became harder to find. Migration routes that had been used for generations became impassable, or no longer led to good feeding grounds. The genetic diversity of isolated populations began to decline as inbreeding became more common. The overall health of populations likely deteriorated as nutrition worsened and competition for remaining resources intensified. But climate change alone may not fully explain mammoth extinction. After all, mammoths had survived previous periods of climate change. During the penultimate interglacial period, about 125,000 years ago, temperatures were even higher than they became at the end of the last ice age. Yet mammoths survived that warming. Why didn't they survive this one? The answer may lie in a second factor: humans. Modern humans began spreading across the northern hemisphere at roughly the same time that mammoth populations were declining due to climate change. As humans expanded into new territories, they brought with them increasingly sophisticated hunting technologies and strategies. spears, atlats, later bows and arrows, fire, cooperative hunting tactics. All of these tools and techniques made humans increasingly effective at hunting large game. And mammoths, being among the largest animals available, would have been highly desirable prey. A single mammoth provided an enormous amount of meat, enough to feed a band of humans for weeks or even months. The bones could be used for building shelters and making tools. The hide provided material for clothing and coverings. The tusks could be carved into tools, weapons, and art objects. Direct evidence of human hunting of mammoths is limited, but does exist. Archaeological sites in North America and Eurasia show mammoth bones with cut marks from stone tools, indicating butchering. Some sites show evidence of mammoth hunting stations, places where groups of hunters cooperated to drive mammoths into traps or disadvantageous terrain where they could be killed. Cave paintings and carvings depict mammoths, showing that humans were intimately familiar with these animals and thought about them enough to reproduce their image. In a few cases, mammoth bones have been found alongside human tools and campsites in contexts that strongly suggest hunting. What makes human hunting particularly significant is that it occurred just when mammoth populations were already stressed by habitat loss. A healthy, widespread population might have been able to sustain some level of hunting pressure. But fragmented populations in declining habitats were far more vulnerable. Computer models of mammoth populations during this period suggest that even relatively low levels of hunting could have tipped already stressed populations toward extinction. One analysis found that if each human in mammoth territory killed just one mammoth every 3 years, this would be enough to drive the species to extinction given their already reduced population sizes. If mammoth populations were in even worse condition, perhaps one mammoth killed per human every 200 years would suffice. The picture that emerges then is of a two-pronged assault on mammoth populations. Climate change destroyed their habitat and reduced their population sizes, fragmenting their range and stressing their remaining populations. Human hunting added additional mortality, particularly targeting reproductive age adults, at exactly the time when populations were least able to sustain such losses. Neither factor alone might have been enough to cause extinction. Together, they proved fatal. The extinction of mammoths was not simultaneous across their entire range. Different populations disappeared at different times, creating a pattern that helps us understand what happened. On the mainland of Eurasia and North America, most mammoth populations were gone by about 10,000 years ago, coinciding roughly with the end of the last ice age and the expansion of forests. But some populations survived in isolated refuges for thousands of years longer. On St. Paul Island in the Bering Sea, a small population of mammoths persisted until about 5,600 years ago. On Wrangel Island, a small island off the coast of Siberia, mammoths survived until approximately 3,700 years ago. To put this in perspective, these last mammoths were alive when the pyramids of Egypt were being built, when Bronze Age civilizations flourished in the Mediterranean, when writing had already been invented. They were not creatures of a distant, incomprehensible past, but animals contemporary with early, human civilizations. These island populations, isolated from the mainland by rising sea levels as the Ice Age ended, survived longer, probably because they were initially protected from human hunting, and because island populations can sometimes persist in stable conditions, even with reduced genetic diversity. but they too eventually disappeared. The St. Paul Island mammoths likely died out due to a combination of drought that reduced freshwater availability and habitat changes. The Wrangel Island mammoths showed evidence of severe inbreeding in their final generations, with genetic analysis revealing harmful mutations and reduced genetic diversity. Whether they died out purely from these genetic problems, or whether human arrival on the island in roughly the same time period contributed to their final extinction, remains debated. The loss of the woolly mammoth and the other Ice Age megafauna had profound effects on the ecosystems they left behind. Without the constant grazing of mammoths and other large herbivores, the character of northern landscapes changed fundamentally. Trees and shrubs that had been kept in check by browsing spread across regions that had been open grassland. The productive mammoth steppe gave way to the less productive tundra and boreal forest we see in the Arctic today. Nutrient cycling changed as the dung and bodies of large animals no longer fertilized the landscape. The entire ecosystem reorganized in their absence. There is something deeply sobering about the extinction of the woolly mammoth. Here was a species superbly adapted to its environment, successful for hundreds of thousands of years, living in harmony with the ecosystem it helped create and maintain. Yet, when conditions changed rapidly, when its habitat transformed faster than it could adapt, and when a new pressure from human hunting was added to these challenges, even this successful species could not survive. The mammoths are gone, leaving behind only bones and tusks, frozen carcasses emerging from melting permafrost, and cave paintings showing us glimpses of what we lost. Their story is a reminder of how fragile even the most successful species can be when faced with rapid environmental change and increased predation. It's a lesson that resonates powerfully today as we face our own period of rapid climate change and witness the extinction of species around the world. The mammoth's extinction was the last of the great natural extinction events, the final chapter in the age of Ice Age giants. In the relatively short time since their disappearance, humans have become the dominant force shaping life on Earth. The world the mammoths knew, that cold grassland teeming with massive animals, exists now only in the fossil record and in our imaginations. But through science, through the painstaking study of bones and teeth and frozen flesh, through analysis of ancient DNA and careful reconstruction of past climates, we can still learn their story. We can still understand, at least in part, what it meant to be a woolly mammoth walking across the frozen steppe. If you found yourself drifting through this journey across the Ice Age alongside the woolly mammoth, if the image of these magnificent creatures has sparked something in your imagination, consider leaving your thoughts in the comments below. What other extinct animals would you like to explore? What questions do the mammoths raise for you about adaptation, survival, or the fragility of even the most successful species? And if these quiet explorations into the natural world help you unwind at the end of your day, please subscribe to Bedtime Biology. Each video is a doorway to another wonder, another story written in the fossil record or the DNA of living things. Until next time, sleep well, and may your dreams be filled with the gentle trumpeting of mammoths walking across endless snowy plains under the Ice Age sky.